This video is going to be about the Unit 6 review. So these beginning questions are all pretty much filled out here for you in words. I don't think there's a lot else to say other than what I've written here. So you can take a moment to pause the video at certain points or find the PDF key online and look through that and read through these explanations, and if the answers to any of these give you any trouble or confusion, come in and ask me and we can explain them further. But I think what I have written here in these should hopefully make sense to you, and as I said, if it does not, make sure you come in and ask. Okay, jumping here to problem number 6. It says, use the rule of thumb to determine whether the following substances would form ionic or covalent bonds. The rule of thumb says that two nonmetals will form covalent bonds and that a metal and a nonmetal will form an ionic bond. So S and Br, S is a nonmetal, Br is a nonmetal. So that's going to make a covalent bond. For Cu and Cl, copper is a metal, chlorine is a nonmetal, so that's going to make an ionic bond. AgNO, silver is a metal, oxygen is a nonmetal, so this is also ionic. All right, then as I said, you can kind of just look over the rest of these questions here and, write them down. Ask me if you have any questions about them after you get done with that. All right, the back section here requires us to make some more Lewis structures. I'm not going to make the Lewis structures here. I'll just sort of show you what they look like in the end. If you would like extra practice on that, I recommend you go back and watch the individual videos that are about making Lewis structures. There's one for covalent substances, there's one for ionics, and there's one for polyatomics. So this first one, N2 is what we're making a structure of. What that looks like is it's an N with a triple bond to N, and we've got pairs of electrons on both sides. All right, this is a covalent substance. We know this because it's got two nonmetals, so that's what resulted in those covalent bonds that we have there. The shape, it's diatomic, because it's just got two atoms in it, so we call it diatomic linear. There are no bond angles. All right, and for the polarity, this one, so it's linear, we have to check for polarity. Both of these are nitrogen, which means they're not going to be pulling the electrons to either side. This is a symmetrical atom. It's linear and it's symmetrical, so that means that it is nonpolar. All right, HCN, that's an H, single bond to a C, triple bond to an N. All right, there's a pair of electrons there on that N. And so this one also, I should have said, is covalent. We know that because it's all nonmetals involved here, which means that we're going to have these covalent bonds that exist. When we think about the shape on this one, we have to look at the central atom. That's carbon in this case. It's got two electron domains on this one. It's got a single bond and it's got a triple bond, so that's two domains. Both of them are bonding domains. If you look up the shape, you should see that that is linear. All right, and the bond angles are 180 degrees for something that is linear. This one is linear, so we check to see if it's symmetrical. It's got an H on one side, it's got an N on the other side. That is not symmetrical, so that means that there's going to be an uneven distribution of electrons in this, which means that it will be polar. CBr4. So there's a carbon, we've got bromine. This is another covalent bond because we've got just nonmetals here. Bromine, bromine, bromine. All right, so that's what that one looks like. If you look at the central atom here, in this case, again, it's carbon. It has 4 domains around it. Those are 4 single bonds. The carbon has no electron pairs on it. All right, so 4 bonding domains, no electron pairs. The shape that you should identify is that it is tetrahedral. Tetrahedral is a shape, oh sorry, I should say it's 109.5 degrees for that one. Okay, so tetrahedral is one of those shapes where you need to decide if it's symmetrical or not. This one has bromines all the way around the outside of the carbon. That means it is symmetrical, all right, because it's all the same atom all the way around. So that makes this one nonpolar. NO2 minus. This one is a polyatomic. You can tell that because it has this charge up here, which means that you need to do that whole valence, find the valence electrons, find the octets, do octet minus valence plus the charge over 2, figure out what sort of, how many bonds it has. When you do that, you should figure out that it has 3 bonds. So we put the N in the middle. There are a couple O's. So we've got an O here and an O here. And then there need to be 3 bonds involved. So I'm going to do 2 here and then 1 over on this side. Then we fill in electrons as needed to make octets. All right, it looks like this. All right, and then you throw the negative sign up here. This one for its shape, you look at the end. You look at the N. It has 3 domains around that N. There's a double bond, there's a single bond, and there's an electron pair. Of those, two of them are bonding domains. That's the single bond and the double bond, and then 1 is an electron pair. So 3 electron domains, 2 bonding domains, 1 electron pair. The shape there is bent. This is the bent variety that's 117 degrees. All right, now though, in terms of polarity, this one doesn't fit well into polarity categories because the whole thing is negative, all right, because it's a polyatomic ion. That whole thing takes on a negative charge. And so I put this in a special category that I call polyatomic negative. So that means it's not really polar because something that's polar has a positive pole and a negative pole. This one is just negative. All right, so it's a charged ion, and that's what it's like. Okay. Thiocyanate. This one here, there are a couple of ways that this could look. One of them, you could have it drawn with an S, single bond to a C, triple bond to an N. All right, and then we would have electrons in these places, have a minus charge. The other way that's acceptable is that you could have S double bonded to C, which is double bonded to the N. All right, and then this would have something like this. For some reasons that are pretty technical, you can't actually have the single bond be between the C and the N. It just makes N act too much differently than nitrogen would normally act. But I won't get into that too much with you. This is a pretty complicated one, so usually there's only going to be one option on these, and you'll figure out what that option is. And so I just came up with this one so that we'd have some variety on here, and as I said, there are a couple different possibilities for this one. But the main point here is that you can come up with a shape from this. If you look at either one of these around the carbon, there are 2 domains, all right? Both of them are bonding domains. That makes this a linear structure. If it is linear, that means its bond angles are 180 degrees. All right, and then again, this one is a polyatomic, so it's not really, it's not polar, it's just charged, it's just negative, so this one is a negative polyatomic. Okay. CSBr, this is cesium bromide. It's an ionic substance, so the cesium is going to give its electron to the bromine. What that results in the end is this bromine has an extra electron, so it has a negative charge. The cesium has no electrons on it, so it's a positive charge. All ionic substances form crystalline lattice structures for their shape. They have no bond angles associated with that, so there's nothing there. All right, and then in terms of their polarity. All ionic substances are polar. They're all actually very intensely polar. So we know if it's ionic, that is definitely polar. H2O. Looks like this. You should look at the domains. It's got 2 bonds around the oxygen, 2 electron pairs. That's 4 total domains, 2 bonding, 2 electron pairs. That has a shape of bent. All right. The angles on this one are 104.5. And then something to talk about, all bent and all trigonal pyramidal, those ones are always polar. So if it's bent, it's polar. This one is bent, so it is a polar molecule as well. Because if it's bent, by definition, it's not symmetrical. So, all right, I went through all that pretty quickly, but hopefully you've done all right on this review. Make sure that you study your notes, look back through all of the old stuff. You know, don't just rely on this because this is meant to help, you know, bring up a lot of these things. But, you know, nothing takes place of looking back at all your notes and giving them a good read through again. So I suggest that you do that. And as always, if you have any questions, make sure you come in and ask.